The next series of short videos are about active filters. In this first video, I want to introduce the concept of an active filter and explain the differences and the advantages and disadvantages of active filters compared to the passive filters that we've seen before. First of all, what is a filter? Well, a filter is any circuit which takes an input and gives an output which has either a gain or a phase, or usually both, which are a function of the frequency. If the filter gives a larger output at low frequencies than it does at high frequencies, as this one does, then we call it a low-pass filter. Circuits which give a higher output at higher frequencies than they do at lower frequencies is known as a high-pass filter, and circuits which give low outputs at both high and low frequencies, but a bigger output somewhere in the middle, are known as bandpass filters. I'll mostly be talking about low-pass filters in these videos because they are the most common and the most useful types of filter that we'll be coming across. The circuit in this simulation is a simple low-pass filter. It has a large output, approximately 1 or 0 dB at low frequencies, and attenuates the signal much more at higher frequencies. If we analyse the frequency response of this, we would find it had one pole at -1/RC radians per second, and it has no active components, in the sense that there are no components in that circuit which require a power supply. This makes it a passive filter. Contrast it with this circuit. Now this circuit also has a single pole in its frequency response, but it contains an op-amp. That's an active component that requires power. So this is an active filter. Its gain and phase response are functions of frequency, but it requires a power supply to work. It's clearly a more complicated circuit than the simple RC circuit that we saw before, which raises the question, why would anybody build this circuit rather than just use a much simpler passive filter which doesn't require a power supply and will be much cheaper to build? Well, you might be able to see one reason already, and that is at low frequencies, this filter has a gain of 20 dB. Active filters can provide gain as well as this frequency-dependent response. There's another reason as well, which would become apparent if I add another component to this filter. At the moment, the output of this filter is just driving an ideal voltmeter, which takes no current. Now, if I wanted this filter to drive another circuit, then that other circuit would have an input impedance. Supposing I add a 1K resistor to represent the input impedance of the next circuit. The frequency response doesn't change at all, because the output of this active filter is coming directly from the output of an ideal op-amp, and an ideal op-amp has a 0 output resistance. However, if I try the same thing with the passive filter, I'll just put this frequency response in memory for now, so we can compare the frequency response that we're going to get when we add the 1K resistor. And you'll see it's suddenly different. At very high frequencies it's the same, but at low frequencies the gain has dropped by 20 dBs in this case, and the pole frequency has increased significantly. So we've got a very different response from our filter now, depending on what the load resistor that the filter is driving is. So we get quite a different response from this passive filter, dependent on the load that the filter is driving. That's not a good thing, because quite often when you're designing a filter, you don't know what the input impedance of the next circuit along that you're going to drive is. With the active filter, though, that doesn't matter, because the characteristics of the active filter don't change with the load impedance there. This particular active filter takes some current from the input. So if there was another resistance here on the input, then the overall gain of this filter would change. But the pole frequency wouldn't, because the pole frequency is just determined by this feedback resistor and this capacitor. We can design active filters, for example this one, which take no current in from the input, because it's going directly into one of the inputs of an op-amp, and which do not change their performance if you added a load resistor on the output, because it's being fed directly from the output of an op-amp, and the output of an ideal op-amp has a zero resistance. The disadvantage of this configuration, however, is that the minimum gain of the op-amp doesn't keep going down forever. It kind of rolls off, in this case to 0 dB, because for a non-inverting op-amp like this, you cannot have a gain of less than 1. So to summarise, active filters have an advantage over passive filters in that they can provide a very low output impedance, which makes the performance of the filter independent of what load that filter is driving. They can also provide some gain along with the filtering action. The disadvantages include the fact that they need a power supply, and any active component is going to introduce some noise. And if we're using a power supply with an op-amp like the circuits we've seen, that limits the maximum signal amplitude that we can get from the filter, because an op-amp can never give you an output voltage outside the range of its power supply. Okay, that's a quick introduction to active filters. Next time we're going to look at second order filters in particular, and we'll come across another quite important and significant advantage of active filters.